Okay, well, thank you for joining me for a few minutes to look at the alternative definition of a derivative. I wanted to look at just the concept as well as three quick questions to remind you what's happening and how we can play that out. Um, this is actually not the normal way people actually teach derivatives. Because really it's not as powerful as the other one, but I really do like using this. So anyway, we'll go ahead and take a quick look at this. I'm going to go ahead and bring my screen over here so that I'm looking in the right direction. But the idea here is that we have some curve, and I have got some point C that has been anchored there, C comma f of C. I literally think about it as like nailing it to the curve. And I want to try to estimate the slope of this curve through that point based on this secant line. So keep in mind, x and f of x could kind of move, and we're going to kind of look at it. And so what happens is if you took f of x minus f of c all over x minus c, that is my delta y over delta x. That's my rise over my run that we're looking at. That would be the slope of this particular curve coming around that value. Now, this would be what we would call AROC, or the average rate of change, meaning x and c is anchored, but x is allowed to move. So I could find the slope between c and any other value on the curve. But then if we go ahead and take this same thing and we add a limit to it, this is the formula that we're actually using. And that would then be the instantaneous rate of change at that value C, because we're literally dragging the value X closer and closer to C. So what I did do is I made a quick Desmos thing out of that. And here we go. So in Desmos, I've got this curve, and I just picked a simple curve, the square root of X, right? And I've got this value right here that I anchored, which is 9 comma f of 9. That's my C value that I'm referring to. And instead of saying x comma f of x, I used a comma f of a, so that value can move around. So I've got all of these various secant lines, but what we're doing is on that first curve, I'm finding the slope of every line that we have. But as soon as you put that limit, what we're doing is we're taking this value and we're sucking it closer and closer and closer and closer to where basically those lines cross. Now you'll notice if I let them touch, it disappears because that's our removable discontinuity. So we just want to be a tiny, tiny little bit off of that value. And now we've got this limit, and that's going to be a tangent line to that curve, okay? So that's what we're going to look at as a couple of problems related to that. All right, I'm going to get pause for just a second here. So now let's go ahead and take a look at a couple of quick questions. I don't think these will be very difficult, but I wanted to show you that when you have certain polynomials, this particular one would be super difficult with the formal definition using h that we've talked about in class. But when we're utilizing this particular version, it's not so bad. So keep in mind, we're going to do f of x minus f of negative 1 all over x minus negative 1. That's that version. Now, this would be AROC. And as soon as I put a limit in front, it becomes IROC, or that instantaneous rate of change. I'm going to switch colors here because I think that pen is dying. So what we have is f of x, which is 2x cubed minus 4x plus 2. And then I need to find out what f of negative 1 is. So I'm going to go out to the side, and if I plug in negative 1 and I cube it, I get negative 1. That's a plus 4 and a plus 2. So it looks like I got a total of 4. So I've got f of x minus f of negative 1 over x minus negative 1. Now, one of the coolest things about these things is that I've promised you already that if you have done this problem set correctly, it will factor. And in fact, that value down there, as you go to negative 1, will be 0 divided by 0 because of how that works. So what we're going to do is let's go ahead and apply that limit. But because we have that foreknowledge that it will factor perfectly, even though this may be a difficult one to factor, I know I've got 2x squared to make 2x cubed. I know that I have -2 to get a -2 here. I just have to decide really quickly, what is it that's going to make this middle term right here? So I need the x squareds to go away because according to what I see, I don't have any. So I've got a 2x squared here. So I would need a -2x here to make a -2x squared. So I got a 2x cubed. I have -2x squared and +2x squared, which cancel. I've got a -2x and I've got a -2x, which makes -4x. So it looks like I did okay. So clearly those things are going to cancel as long as I don't literally touch that value. Like you saw in the video, as soon as I touch it, it disappears. But if I get infinitely close, it's still there. And so as I get super duper close to -1, then I'd have 2 times -1 squared. Now remember, that's one of the rules of limits is go ahead and plug in the number and see what you get. And since we made those values disappear, we actually can, in fact, do that. And so I found that the slope of that particular tangent line would be 2 around that value. The bummer is that only gives me that number at the number -1. And if I wanted to now find the number at 5 or 7 or -6 or the square root of 3, I have to start all the way over, and I glean no extra information, which is why a lot of people don't teach this. But sometimes, in fact, frequently, all you need is one number. And if all you need was one number, it's a great way to do it. Okay, now a radical is another one. So keep in mind, we want to know what f of 2 is, and I purposely made this one kind of a little bit less pleasant. So I'm going to jump right to the full story. Let's take a limit as x goes to 2. I'm going to have x minus 2 in the bottom because remember it's f of x minus f of c all over x minus c. Now we've done this quite a few times now by this point in time in your career in my classes. Is you're going to go ahead and use the conjugate of the portion that has that root. So I'm going to go ahead and do this. Now, I purposely made this problem not at a number that would be nice. I mean, usually we would ask you something that actually comes up pretty kind, like 5/3, where you would get the number 1, but I wanted it to be a little bit uglier. So remember, one of the principles is that we were attacking the numerator of this problem. So we are going to leave the denominator exactly how it was because our guarantee is that x minus 2 is going to cancel out. And so I want to leave it in factored form so it has that ability to cancel out. Now, when we do our distributive property, I'm going to get a 3x minus 4. This term and this term are both going to cancel out by the very design of what a conjugate is designed to do is I've got negative root 2 times this and then negative root 2 times the same thing. And then, of course, this product is -2. So if you look at it, my numerator right here is really 3x minus 6, which is absolutely fantastic because, of course, now you can see if you factor a 3 out, we get x minus 2. So I took a problem and I purposely designed it to be as bad as I could be. I made it come to a value that was at a root, but I can't really make it work any way other than what's fairly nice. So as I get really close to the number 2, the numerator is a constant. It's 3. I can't do anything with it. If I plug in 2 right here, I get root 2 plus another root 2, which is 2 roots of 2. I'm done. Again, because the whole idea in limits, as soon as you make that removable discontinuity disappear, we can actually do it. And remember, a limit says what happens is you get close on both sides, but you don't technically touch that value. I'm done. Okay? Now, the last one that I was going to look at is I wanted to do a polynomial. I wanted to do a radical. And then I also wanted to do a rational. And so again, we'll take a look at the limit as x goes to c, which in this case is 5. I'm going to do f of x minus f of 5 over x minus 5. Again, just doing the nice, easy way. Now, f of 5, I think I designed this one to not be perfect either. That would be 25 minus 1, which is 24. 2 times 5 is 10. That's 13. Again, That's a bizarro value. I want to find out what happens if this curve at 5, 24/13. What's the slope at that value? That's strange, but no big. What we're going to do is then we're going to take f of x, which is the original problem, as it states, minus 24/13 all over x minus 5, and we're going to take the limit as x goes to 5. Now, of course, we want to do our nice little fraction buster. So I'm going to hit the top with a 2x plus 3 and a 13. I'm going to hit the bottom with a 2x plus 13 plus 3, and a 13. And as soon as you start distributing, this piece is going to cancel with this piece, and I still have my 13 attacking the 5x minus 1. The 13 here is going to cancel with that 13, and I got my 24 with my 2x plus 3. Down here, we're going to leave my x minus 5 because we know that that somehow has to cancel out. We've been promised that. So let's see what happens. So I see 65 x's minus 13. I see negative 48 x's and a minus 72. So putting that all together, let's see, what is 65 minus 48? I feel like I should have that, but I certainly don't want to mess my video up and have to start over. So I got 17 x's. And negative 13 minus 72 is negative 85, which is 17 times x minus 5, okay? So I'm just doing a little bit of side note here so I don't have to write everything a second time. So my numerator is 17 times x minus 5, and my denominator, of course, is x minus 5, 2x plus 3, 13. So, of course, as I get close to 5, we know that the numerator is, 17. Why did I guess I got the number 5 in mind there. That's 17, and if I get close to 5, I'm going to get 13 times 13, because 2 times 5 is 10, plus 3 is 13. Hey, we got a slope of 17 over 169. Now, what you can do, which is a little bit interesting, is if you go back in here into Desmos, we can validate that solution pretty nice in the following way. I'm just going to go ahead and clear all these things out because we can. And let's make our original function here 5x minus 1 over, let's do 2x plus 3. I'm curious as to what is happening around the point 5, 24 over 13. So you notice our little dot there. And according to this, if I do y minus the y value, which is 24/13, equals, let's see, x minus the x value, which of course was 5. And then I institute that slope that we just got from our instantaneous rate of change equation, 17 over 169. What you find out is, in fact, that did hit that graph absolutely spot on perfectly. All righty. Hopefully that's a little bit of a help. Again, a great way to do a problem if all you need is an individual point. And I'll be back for a different video where we talk about it, where we have the generalized version for all values of x and all values of h. Okay.